Texas Lutheran University.
It's a privilege to be here, and I appreciate the opportunity to tell you what we're doing. Thank you, Dr. Gray and Dr. Thompson. So I've got a big title, and I'll tell you a little bit about what this means, but two-dimensional nano architecture for enhanced energy storage and conversion. But let me tell you, as we're going through, I'm going to give you kind of just a high-level background on my background and what we're doing a little bit. And I just picked two areas that we've done some work and published some papers in. Since I thought I'd talk about our work with vanadium pentoxide polymer nanocomposites for improving magnesium ion charge, storage and transport, and then I'm going to talk to you about some new ways we've developed some catalysts for, in this case, fuel cells for electrochemical oxygen reduction, and then I'll give some acknowledgments. I wanted to give a little bit of a background of where I came from. So I'm just down the road right now, but I started out, I actually grew up in Houston, and then after that, didn't know what I wanted to do with my life, got my degree, actually went to, first actually Colorado, then to Arizona. I worked as a high school science instructor after getting my degree, so, and then I decided, you know what, chemistry is kind of interesting, maybe I should go back, and I decided to get my PhD in Oklahoma. And then after that, I went to UCLA, and then I went to Washington, D.C., where I worked at the Navy for 3.5 years, and then I worked in a company for a college station for about 9 years, and then I started here at Texas State back in 2014. So I'm showing you this, and I drew a picture here. There's a triangle, and there's two things in here. Number one, this is not the well-known Bermuda Triangle, which is actually maybe the older generation of us a little bit more used to talk about the Bermuda Triangle. So this Bermuda Triangle is over here. You can see a clearly different shape. And this is an equilateral triangle, right? Mine is not an equilateral triangle. You can clearly see the different shape and location. So I also just want to mention, you're going to take your own path for whatever you're going to do next. And so you can see I lots of different things. And so as you go through your journey, your life, your career, take the opportunities you have and learn what you have here, and that'll set you up for the next step. Sounds like a great things that are going on here. So the next thing is, if you can, and during your opportunity, see if you can find something that interests you, maybe even you're passionate about it, you have some level of interest. Because if you want to do something for a long time, it takes a lot of work. So if you can like it every once in a while, it might be a good thing. All right? I'm not expecting you to like it all the time. It's still work. But see if you can find something. So one of the things that interested me all the way back from when I was in undergraduate was taking care of our environment. I was a big, actually, in back to this, I was really wanting to do things that would help and be responsible and help improve. So I decided, as I was continuing on, that I really thought one of the ways I could contribute was in making energy materials for energy applications. So I want you to look at, this is from just the projections of the world energy consumption, and this is broken out into two groups. You can't quite see the colors, but this is blue. This is actually a French pronunciation here, so I'm not going to try it, but basically this stands for developed nations, the 35 industrialized nations, the United States, only one. So it goes up a little bit, but you can see this trend here, the overall trend is what? It's going up, right? We're getting more and more energy. We're going to need more and more energy, and especially the countries that are developing are going to need more and more energy, right? So this is pretty clear to me when I was actually in Haiti, and I was sitting there, and a number of different times that I visited there, and they were in the process of trying to get their energy, and as we sat there, we're trying to use our internet, the things would go down, and I thought, oh my gosh, there's no way. We're going to need a lot more ways to store energy and capture energy. So think about what we use energy for, and here's some examples. Driving a car. I don't know if anybody has one of these things. I'm guessing you probably do. Your homes. I had a hard time thinking what we don't use energy for, honestly. So you're using energy in all the different things we do. We have lights going on. Everything that we're using, we need energy. So, so the big question I think I'm asking is how can we store, how can we convert and generate energy that's more efficient, right? That's cleaner, that's safer, that's less expensive. So those are our big goals that we'd like to achieve. And so many of you are probably aware we can do these things if we use things like renewable energy technology. We make better batteries, capacitors, fuel cells, electrolyzers, photovoltaics. There's lots of opportunities. But underneath each of these, to achieve these big goals, under each of these is a whole set of materials. We really need to understand the materials in these to be able to develop things that will be more efficient and cleaner, safer, and less expensive. So this motivated my work, and so broadly the area, and I and many of other people have been working in for a while, is the area of nanomaterials. So actually a physicist, I just want you to like this, back in 1959, Richard Feynman gave a seminal talk entitled There's Plenty of Room at the Bottom. And so he opened the door for some thinking and stimulated the thinking that he could possibly have direct manipulation of individual atoms. Wow, that was pretty groundbreaking to think at that time. So he's considered sort of a pioneer in the area, one of the fathers perhaps of this area of nanotechnology. And so since that time there's been lots of different nano materials such as nanoparticles or clusters, nanotubes, and now more recently nanosheets. So this is nano, of course, is Greek for dwarf. This is the word, we're not talking about the dwarfs perhaps in the some of the movies. We're talking about some little small things here, but at least one characteristic length scale less than 100 nanometers. And so one of the big qualities that we have in nanomaterials is we have a ton of surface. All this surface is available for us to do reactions with. We also have unique structures that can be present. We can have different structures at the surface that are different than in other cases. And we can also have very unique and distinct properties that can be different than an individual molecule or a bulk material. So one of the materials that was particularly interesting is graphene, right? It's a single layer of carbon atoms, and so this broadly was after being discovered or perhaps just recognized well in 2004 by Daim Vosilev and co-workers, for which they won the 2010 Nobel Prize. There's a whole host of materials that make single layers of atoms together, and so maybe many of you have heard of these, but you can make this with lots of other materials rather than carbon, such as molybdenum sulfide, boron nitride. And so why are we interested in some of these types of materials? Well, the electrons are actually confined in those layers, so we can get things like quantum confinement effects, and we can get orders of magnitude higher electronic conductivity. We can have these surfaces that are exposed. We can have edges here that can be reactive. They're highly anisotropic in their properties and strain and very high surface area. So one of the questions that you can ask is 2D or not 2D? That is the question. And so when I was in the company and working last, I thought, well, sounds really cool. I think we'll get some of this. We'll try to make it. It's extremely hard. And we ended up buying it, and as we tested it, it was poorly. It performed very poorly, and I was somewhat frustrated and disappointed by the promise of this and the fact that, yes, we can see these beautiful pictures, but yet it didn't actually perform well as we needed to use it, which was in a 3D structure. So many materials are not really 2D, and so we wanted to obtain a 3D structure that retains the features of a two-dimensional material and look at other compositions to see if we could make some improved energy materials with this. So my group, as I started it several years ago, I thought, well, let's take this theme, let's take this challenge, right? So I want you to see some of these research problems as a challenge, right? We're going to see, all right, just because there's a problem, let's see if we can address it. So I decided to take a look, and this is one of a number of different materials we looked at. So here would be a two-dimensional layer, single layer of atoms. In this case, we're looking at vanadium pentoxide, and I know these little things are a little funky, but you're used to seeing a tetrahedral and things like that, right? So in the middle of this thing is a vanadium, and you have a bunch of oxygens around it. So we have single layers of atoms, but rather than a single layer, we're going to put this into an overall material, a three-dimensional structure, which we're going to call a nano architecture. And the reason why we're calling it that, and so we've got some earlier work on this, is because we're going to think of the word architecture and used in a sense of material, but where do we usually hear that word used? buildings, right? That's a word that we use to describe a building, and that's telling us we're designing a building with certain functionality. We're going to design that building. In this case, you can see that this building's designed. We have walkways, we have areas where we could do things like pizza, right? We can, there's spaces, we're sitting in a place, we're looking at something, so there's a design for not only, there's space within that, but be able to accommodate people in the movement of things in that building. So we can apply that same thinking to a material where we're designing it with solid and core networks. And so we have an interconnected solid network and an interconnected core network, and that allows things to go to that surface region. So again, we wanted to take this approach and see if we could make these types of materials, and this would give us some better properties, and perhaps we didn't understand things a little bit better. And so again, these are our broad goals. Can we synthesize? Can we stabilize these? What are the structures, and how do we do what are the properties? And so this is a standard material science, kind of a triangle where we're understanding the relationship between center and structure and properties. We're trying to develop correlations between structure and properties to understand what structure gives us the right properties, how we synthesize it. And so these are sort of big challenges that we were doing. So can everybody see this okay, or should I turn the lights down a little bit? I'm going to show you some other pictures. Turn it down a little bit, okay. All right, if you fall asleep, raise your hand, okay? Right. So I'm going to show you some nice pictures that we got. This is with our scanning electron microscope. So here's some of our family, and I didn't show all the pictures. Some of them are young and they haven't yet made it, got their picture taken yet, but these are some of our transition metal oxide or hydroxide two-dimensional nano architectures. Here's iron oxide nanosheets. We just published some work in this. Here's some vanadium oxide nanosheets, nickel hydroxide, cobalt hydroxide, titanium dioxide. So we can make a lot of these different materials with sort of structure, and you can see these sheets, and I'll show you some more pictures of these. So I'm just going to tell you about a couple of the stories that we've done, and I'm going to skip lots of things, but I'm going to tell you just about this story here, how we've used vanadium pentoxide nanosheets, and then I'm going to tell you one story about how we've taken nickel hydroxide and turned it into a very useful material. So first we're going to talk about one application and how we would create a two-dimensional nano architecture for energy storage. And so I'm going to give you a little background, and then we're going to talk, and I'm going to weave you back into a little bit about that material. So first I'm going to introduce magnesium batteries, how battery works, why I would be interested in things like magnesium. And I and many other people looked at multiple electron charge storage materials. So we're trying to take advantage of multiple electrons per center. And so if we think about these divalent, and in this case trivalent cations, each one of these reactions involves 2 or more electrons per ion. Okay, so in this case, if we just look at magnesium, and let's compare that for lithium, which is what you actually have in your cell phones now. So rather than 1, the cation valence with a +2, so that's good for us because we can get 2 electrons instead of 1. The voltage isn't bad. More negative in this case is good, so it's not that much. We lose a little bit of voltage, we're still okay. It has a actually very high volumetric capacity and reasonable gravimetric density, but it's also, you can look at the natural abundance here. We have orders of magnitude more magnesium than lithium, so that's good. So the cost is significantly lower. So there's some positives there and also some challenges. So the potential is we could get reasonable voltage, lower cost. And there's a real problem when you always see those, probably heard about those batteries that catch on fire, right? So lots of those are because these little dendrites form with lithium, and they actually short the battery and things, and it doesn't like to be like that. It doesn't like that, right? Lots of heat gets generated and it gets on fire. So we don't have any dendrites in these kind of things, so that's an improved safety. So we're going to focus on the cathode material. We're going to put a magnesium metal here. We're going to have an electrolyte where magnesium ions can move back and forth. And then we're going to look at this cathode side. So in this case, we'd be looking at a cathode material. If we were discharging it, we'd be putting a magnesium ion into this cathode, putting 2 electrons into that. And then we want a host lattice that would able to accommodate the magnesium ions and the electrons into the structure. And so there's been lots of work done before to try to demonstrate that this kind of a a cell and a cathode could be made, and there was some early work done. Lots of different materials have been investigated. However, there really hasn't been a good approach for getting very high capacities, good voltages, good reducibility. You can get it in, but you can't get it out. And as well, rate capability. You want to do it fast as well. So we took a look at vanadium pentoxide as sort of a versatile cation host material. And here's a picture of the crystal structure of vanadium pentoxide in the crystalline phase. And so one of the nice things about this material is we have multiple oxidation states. We can have 5, 4, and 3. So that means if I would put an electron into that vanadium center, then I can accommodate magnesium. And it's got a nice layered structure. And other people have said, yes, this is possible to do that. So I was going to, again, here's our equation. If we take a V2O5, we'd be putting a magnesium ion, an electron, and then we would insert that magnesium somewhere into here, and we would get a change in the oxidation state of the vanadium as we put that ion into that lattice. Now let's go back and look at the lithium and magnesium, because now it becomes more challenging. So these have the same valence, and initially, if we look at the ionic radius of these don't look bad. They kind of look similar. If you remember back to maybe general chemistry, if you talked about the different radius and things like that. But the charge density is different. So if we have the same radius, we have 2 charge, we've got a lot more charge density. And so it wants to compensate that charge. It needs to interact with something else. All right? So it wants to, that positive charge is going to have a strong interaction with, in this case, the negatively charged host lattice here. And that's going to lead to some challenges. And in this case, we can see this sort of challenge if we look at the way that strong interaction is not going to make it easy for you to get migration through the lattice. You're going to be strongly interacting. If you're sitting there very strongly interacting, it's going to be hard to move that ion in the lattice. And so this is some calculations done by the Cedar group, just showing, in this case, it's easy relatively to put a lithium ion through, but you can get a significantly higher activation energy as you're trying to move through that lattice, okay? So, there's some nice work done. If you put water in there, well, that's great. Water, you can compensate some of that charge between the lattice and the magnesium ion. If the water is donating some of its electron density to it, that makes it easier to coordinate, and the diffusion is much better. Unfortunately, and so you can get very high capacity, so 250 is a really good number, okay? And so if water's in there, that's great, we can get more water in there. Unfortunately, for the other side of the reaction, the anode, it doesn't allow the magnesium metal to strip, so it's a non-starter. You can't use the water in there if you actually want to use metallic magnesium. So all the benefits that we talked about, you won't realize. So if you take the water out of there, well, you get very low capacities. So our challenge was this: can we rethink of a layered material instead of as an sort of assembly of these two-dimensional materials? Can we rethink of these layers? Can we do something to facilitate the way that magnesium would move? And so we could consider this interlayer region here, where maybe we could design that appropriately to be able to accommodate magnesium ions. And so we thought, well, one of the things we thought of is let's put a polymer in there. These polymers, such as like polyethylene oxide, they've got an oxygen in there, so they can sort of act like water in the sense of having electron density, negative charge. It can coordinate. These are actually fairly good ion conductors by themselves, and so some other work has been done. We thought, let's put a polymer in there and see if we could get any improvement. So just to walk you through a little bit of the chemistry here, we can form these vanadium pentoxide nanosheets by water addition and condensation reactions. We form aqueous vanadic acid by using an ion exchange route from sodium metavanadate. And then the critical reaction here is once we form these species with the OH groups on them, then they can undergo a condensation reaction here where we're losing water and we're forming a bridging oxygen. And so they like to form these nice layered sheets. I don't have to add anything in there, that's just how they like to form because of the partial negative and partial positive charge between these. So we said, well, we can add a nice solution, we can form these kind of sheets, let's just throw our polymer in there and let's see what happens. So we put the polymer in the solution, And then we let it react. It actually formed an interconnected network there. And so I'm putting this in blue because it's kind of got all this stuff inside of it. We don't know exactly what the structure all is. We used a thermogravimetric analysis to figure out how much polymer and how much water. In this case, we used PEO 1 and 2. This just meant this one had a certain amount of polymer in there relative to the V2O5, and this one had about 4 times more, about 1.2 formula units per V2O5. And what you'll see, and I'll come back to these, both of these actually still retain some water in the structure. Here's some more images. You can see sort of the sheet-like structure here, and some more high-resolution images. We can actually see the lattice spacing here. So you can see if we put a polymer, we increase the lattice spacing. So we go from 8.6 to 9.1 to 10.8. And then we can use a technique like X-ray diffraction. In this case, we're looking at this diffraction between these planes, and this is I'll just talk about this 001 plane, which is the reflections associated with the distance between those planes, the ordering within those planes that we're seeing. And so we can see as we shift, we put the polymer in the structure, this peak went down. And that means the layer's getting bigger. And that's the same thing that we saw with the TEM images. This actually correlated, well, we don't know exactly how the polymer is in there, but these were earlier models that showed if the polymer is sort of making a zigzag in between the structure or making a sort of helical conformation, these actually, numbers actually correlated very well with the spacings that we were observing with our X-ray and our TEM images. So maybe we're something along those lines of how the polymer may conform between the layers. I'll just kind of go briefly. We used infrared spectroscopy. We did ATR. I don't know, I saw one sitting in there. And so we used that too. We needed to figure out what the vibrational bands, the infrared active vibrational bands. We did see the presence of the polymer, these particular COC asymmetric stretching modes with a different conformation than typically in a crystalline polymer. We also saw a shifting of the vanadium oxide stretching mode from the ion, suggesting we're getting some kind of interaction, perhaps the polymer. So Dr. Santi might be interested in the Raman work that she's doing a little bit as well on. So here's some Raman spectroscopy between our vanadium pentoxide, the vanadium pentoxide with the polymer 1 and 2. So there are a lot of just bands. What do these bands mean? Okay, each of these is an individual vibration mode. And so there's a lot of information in here in terms of prior work. We can have internal modes and more external modes, which are long-range vibrations beyond a single unit cell. And so we were like, well, how do we interpret this? What exactly is going on? We looked up some prior work that said there's lots of things that happen when you add water into the structure. And so we started looking at these a little bit, and we found that if we looked at these going back to the TGA, they had the similar amounts of water between these two samples. However, we could see some clear spectral differences. So we decided to let's look at these low frequency acoustic lattice phonon modes here. And so if we take a look at these, and we did, so let's just say we sort of reasonably consider that maybe we'd have sort of 3 sort of dominant bands within this region. And so we decided, well, let's see if this analysis holds any work. And so let's look at this second peak. And so this was in a lattice phonon mode. It's sort of a long-range kind of interaction, restricted translations here. And so this told us there's some information about how water interacts with this single sheet. Okay, and so what we observe here is if you look at this peak 2, we see a significantly different relative intensity. And so if we plot the relative intensities of these bands, we can see the peak 2 decreases in relative intensity. However, we saw the water is the same. Well, how does that go together? And so we thought, well, maybe the polymer interacts with the vanadium layer rather than the water. So if we get these kind of an interaction, then that might explain a little bit of that thing. So these are just postulate mode. We come up with ideas that maybe are consistent with the data. So this is what we think right now might be going on. And we think that the polymer may change the way these specific modes interact and pair with water. So we're still in the process of understanding that. But what we did is we only tested the cell. And so we can see that compared to the V2O5, we have, in this case, capacity tells us how much of those ions, how much of those electrons we can actually store in the material. We can get a lot more with the polymer. And if we look at that original X number, so we can store at least twice as much magnesium ions and electrons in the structure with the polymer in there. And it shows some reasonable stability. Okay, this isn't perhaps the most awesome. This is a challenge. All these are somewhat challenging to get to work, but we got some initial decrease and then we formed sort of a stable structure. I'll sort of just walk you through sort of the results, but we used a cyclic voltammetry, looked at the scan rate dependence. This is what's called a Reynolds-Savage equation, and so we can look at the relationship between the scan rate and the peak current, and we can actually calculate a diffusion coefficient out of this. All right, so we can spend more time walking around. If we actually use this analysis, we can see the slope of this line indicates the diffusion coefficient, and we can see a higher slope here compared with the V2O5PO1, and we can actually calculate a somewhat low but still higher diffusion coefficient with the polymer in there. Now, what you also see is the highest amount of PO actually had the lowest diffusion coefficient. Well, that doesn't seem to quite make sense to us because we're getting everything bigger. So just making something bigger didn't necessarily mean the ions actually diffuse as well. We still don't fully understand that, but this really pointed to us that there's really an opportunity to design that inner layer to be able to accommodate these other ions. So anyway, so there's some possibilities that we can do that work. Okay. I realize that I'm kind of taking too long on this, so I'm going to go a little bit faster on this other part here, and I'm just going to tell you a little bit about briefly how we make these into a different application used for energy conversion. All right, so in this case, we're trying to make something that works for a fuel cell catalyst. So these are actually, here's a picture of a fuel cell in a car. So instead of your battery, maybe you could have a fuel cell in it. Why would you want to have a fuel cell? Because it's more efficient, okay, than an internal combustion engine. So there's a catalyst in here. We can, in this case, the overall reaction is clean too. You can just take hydrogen and oxygen from the air and produce water, so there's no emissions. And so the most challenging reaction here not only is this oxygen reduction reaction. So we're taking oxygen, water, and electrons and making water here. And this is very challenging to get it to work. And so really the best catalyst is platinum, okay? And so despite all the other work, we'd like to get rid of platinum. Platinum still retains the best. So we kind of realized, right, you remember Bugs Bunny? Did anybody watch Bugs Bunny? You know, where there was that guy saying, if you can't beat them, join them. You remember that one? Well, that's sort of where we are with that. We sort of said, all right, let's get on go. Let's see if we can get platinum to work better. And so one of the ways you can do that is if you alloy it with another metal, you stick another transition metal, you can alter the electronic structure, the specific structure of those intermediates, and you can get the reaction to be much better. And I won't walk through all the different reasons for that, but we can. So there have been single crystals that show nice faces. So these beautiful kind of pictures of all these structures that you could create with that. They could get higher activity. They call these nano frames. Fortunately, they all still had carbon. Well, I told you carbon was graphene, and the reason they still had carbon is a matrix. Okay? So let's go back to see if we can do something with our 2D materials, and maybe we could get a face that's highly active and with this kind of a nanosheet structure. And let's not use any carbon, because if carbon, once it gets to grade, it actually makes CO2 if you get to a high enough potential. So the problem is that it degrades over time. And so so that's a real problem. So we took our nickel hydroxide, and in this case, and put platinum on it. And then we heated it up to 200 to 300 under hydrogen conditions. After a little bit of time, it actually forms and makes a magnetic material, indicating probably metallic nickel in there. Here's our structure of this nanosheet. We can actually isolate a single sheet. Here's the sort of structure of that, the crystal structure. I'll walk you through the other data. Here's actually a single sheet. We can see a little platinum aggregates. There's actually atomically distributed platinum here at the surface of that, which we were able to image. And so here's what we're calling our nanoframe. Once we heat it up, we can form what we start out with this, and then we heat it up. I don't know if you can see well, there's little tiny pores and formed in here. I'll show you some nicer pictures of that. And the reason why we heated it up is we said we need to get platinum and nickel to get together. Okay? So the reason, and we have this oxygen sitting between there. So we were really surprised because most of the time everything will collapse when you try to do that. But we actually formed an alloy, and it's stable after electrochemical tests. So here's some really nice pictures that we got. You can see these are layers, and these are actually platinum nanoparticles here. And they actually form, you don't see any distinct particles, they kind of sort of melt into the structure a little bit. And these are high resolution images. I think this is really a beautiful thing to look at. You can just see diffraction around single atoms. Okay, I don't know if you realize you could do that. We can see that, right? You can't see the actual, all we're seeing is the diffraction around the electron cloud, around those atoms, but you know, I think it's pretty amazing. These brighter ones are more consistent with the platinum, right? They have more electrons, and the ones that are not as bright are probably more with nickel, but we can see them. So I'll jump some of the other pictures you can see just so it doesn't take too long. But what I wanted to show you is once we get to the electrochemistry, this reaction occurs at 1.23 volts. So the higher we are towards that theoretical potential, the better. Here's our platinum carbon. We can see this is a higher current. When we normalize that for the area of platinum at the surface, we're very high. The mass activity is not quite as high, but we're actually the best unsupported catalyst without carbon that's ever been reported that we're aware of. Okay, now there's other ones that are using molybdenum and all this other stuff. The challenge with these is they degrade. When you go to a high potential, they've got carbon in there and they're going to degrade. Ours stayed very stable over time. And so this was the highest combined activity and stability that we found reported, and maybe they'll find another way, and that's great. But anyway, that was very interesting, and I put this thing in here because this is where now we need to see what actually dissolves. And so you'd love things to be stable, but what I realized is we realized that go higher potentials and go even higher other applications is there's really nothing that we're aware of that's actually stable under these conditions. Platinum dissolves, iridium, ruthenium, everything that's active actually dissolves. So that's where I'm hoping you can help somebody there. We actually have to figure out, well, how much platinum dissolves, how much nickel dissolves, and so this is where elemental analysis is particularly useful. So we've had to do some analysis. And in our case, we get much less platinum coming off than this platinum carbon, we think, due to this architecture. So I want to just give you an overview of what we're doing, and hopefully I've told you a little bit that you can create some improved materials. We're using this type of a design, such as a two-dimensional nano architecture. Here's the example of iron oxide, where we've made this nano sheet and got much better capacity than a typical nanoparticle. So that's another story for another day. But there's specific opportunities to use this approach, and there's lots of challenges and new opportunities, and so this is some of the work that we've been able to do. And I want to acknowledge our funding from the National Science Foundation, the Office of Naval Research, and also some equipment from the Society of Plastics Engineers, and of course my group. Probably you realize that most of the research happens because students do something, so all of the group here, Fernando, Duop's not there anymore, with Civo, did all the, this is all the catalyst work. Civo and Randall Archer did a lot of the vanadium pentoxide work, and beautiful images from UTSA, and some people also from the Department of Energy lab in Colorado. So before I forget, I want to mention we have a graduate program. So I encourage you, wherever you go, if you're interested in chemistry, you're interested in physics, consider going on and continuing to pursue your education wherever you decide that might be the best opportunity. So I wanted to mention two programs that are available. Texas State, which should be aware, we have a Master of Science program in chemistry and biochemistry. The deadline of this is actually in February, so if you missed the early deadlines, Texas State has some possibilities for you to still apply. So if you're interested, you can follow this email, or you can let me know. I'm Sir Dr. Bray. We have a PhD program as well in Material Science, Engineering, and Commercialization. So it's a little bit different program than a typical PhD program because we help train people on skills that might be useful in a business environment as well as just a technical environment. So you have to have, they're changing some of the requirements to be able to bring bachelor students in. At this point, you need a master's for the program. So I want to say thank you for your attention, and I'll be glad to talk about questions or anything else you want to talk about.
Questions?
Students.
All right, you got to wake up. I know I threw a lot at you, so sorry that was a little more.
All right, you get genuine and analytical. And
Physics professors are allowed to ask questions.
Oh, no.
Please, Doctor.
So I'm curious about you mentioned this two-dimensional architecture, so it looks like you're wanting to, because the vanadium pentoxide seems to form naturally these sheets, so how do you get it to fold or?
Yeah, there's a lot of things that are creating. So we can have an individual sheet. Sometimes they'll like to form layers by themselves, or they can dry into different ways and form a different piece. So it's actually, there's a lot of challenges as we can deal with that. We started realizing, well, the material we made was actually layered. And so it's actually the only material of the ones we work with that's naturally forms a sheet. The other ones you have to sort of put other things in there to help them grow as sheets. I mean, graphene does it by itself as well, but so I think there's a lot of drying forces going on. There's a lot of forces that we've done, and during that process, right? So we can think about in a solution, we have a bunch of sort of sheets that are randomly oriented. As we gradually pull that solvent off, they're going to, depends on how fast, depends on lots of different forces in there that are drying. And so we haven't fully controlled all those things yet. Many of the things have enough porosity in there. That one actually has a very low surface area, and so we haven't tried to sort of, we're in the process of actually trying to create orientation and things like that, but there's lots of forces going on that I won't say that we understand yet that are actually occurring that we can say, all right, can you know, we actually thought, we tried putting little things to prevent them from just sticking together to form different things. So I think there's a whole set of things that need to be done to really create that more in a more controlled fashion to create that area. So it's a really good question.
I have a really big picture energy question. So with all the damage to basically the whole grid wiped out, which our grids we know are not the best design ever.
Yeah.
Do you think it's at all practical to build something different in Puerto Rico, or are we just going to end up building the same thing?
That's a great question. Unfortunately,
I know you're
it's
very
above my
scale,
pay grade, you know, to know what's practical. I mean, I think it's a great, I mean, I would certainly consider that opportunity to do something that's going to be more long-term viable. You know, I would say, you know, places like Hawaii have, an island has been very aggressive in terms of their overall redesign of their grid structure that I'm aware of, and lots of renewable energy and things like that.
People are doing it.
People are doing it, but you know, there's upfront costs, just like you want to put photovoltaics on your house, you know. Nobody wants to shell out the extra money yet, but long term it can still be a benefit. So there's lots of factors in there, and so there's politics and everything else. So
The technology exists.
I don't know that it exists at the level we want. Energy storage is actually a major factor in there. That's actually a huge challenge. The generation of the energy from wind and solar, I think that's actually probably one of the big bottlenecks right now. I was in one of the DOE programs where they were trying to explore that. So I don't know, on a small scale, small microgrids, I think so, but I don't know that challenge. I mean, there are technologies, but I still think they're too expensive. It's kind of the bottom line that it'll probably come up as. My guess is, you know, yeah, since it's not quite ready to go, but hey, we've got work to do, so.
Problems to be solved by future science.
And you can make a difference, you know, in what you're doing. It may take a while, but you can. Did you see anything you've ever seen before in any of your classes, or did I throw too many things out?
There's lots of stuff you've seen before.
It's familiar.
Okay, yeah, I probably should have like thought, oh, okay, let's go some.
And then they counter all that in organic, so.
Okay, all right. Yeah, I know, I do a bunch of material stuff that you may not know, I should have shown you.
I saw that in all.
But
Yeah.
all the stuff that you're probably learning, is can be a benefit to you. So keep learning, and you can learn how to apply it, and keep learning new things.
I have a
Yeah.
question.
Yeah.
Because you said that lithium batteries can form deuterites and that causes them to overheat and possibly cause fires. You mentioned that magnesium wouldn't form deuterites.
Dendrites. yes.
Dendrites, my bad.
Yeah.
What about the magnesium doesn't allow it to form those?
That's a great question, too. I don't know that I've fully delved into that to know, to be able to answer that question well yet. I would say on the lithium side, what I'm aware of is the reason it forms dendrites, and you see some of the stuff, the Boeing fires and other things like that. And so I'm going to try to answer the question by what I think is happening in the lithium system. So I'm guessing there's something different on the magnesium system. But the reason the dendrites form in the lithium system is there's a charged flux. So that you do things fast, the things aren't able to move fast enough, and so they end up forming sort of these islands instead of having enough of an anion. So there's a sort of buildup of charge that happens in the dendrites, the lowest energy structure that happens. So things like when you do low temperatures or when you do things very fast, that's when the dendrites form. So I'm not sure that I have a great answer for that on the magnesium side because I haven't been looking at it. There's something different at that surface that's forming I guess what I've observed is there's sort of hills and sort of things. I think that my guess is that the energy required to form a new surface is different at a dendrite than perhaps the surface. So you're nucleating, you're doing a nucleation event. Okay, and so there's going to be a different nucleation energy at a dendrite surface perhaps than a more flat surface. So I kind of point to that. There's maybe that. Maybe it's harder to get 2 electrons in that piece than it is when there's sitting down there at a different surface. That's the best I can come up with. But that's a great question. And so some of these questions I don't have answers for, and we don't have, so that's why we're doing research. But I guess somebody's probably looked at that, but I don't yet know the answer to it very well. But that's just my guess. Yeah.
So mine's kind of 2 questions.
Yeah.
You said that one of the reasons that we use vanadium pentoxide is because it has multiple oxidation states, but aren't there a lot of transition metals with multiple oxidation states?
Absolutely. There's lots of metals that have multiple. But what we're most interested in this case, is getting a material that can have multiple oxidation states and still have a good potential. So you can do, again, we had the vanadium is one example, and you're exactly right. There's lots of them that'll do this as well. But the vanadium is pretty high oxidation states. We get 5+. So there's lots of ones. There are other ones, ruthenium, iridium, and things like that. So that's a fairly high oxidation state. So we can go from 5+ to 4+ to 3+. And so we're still can be a reasonable potential. There's other things like nickel. Nickel will do 4+ and 3+ and 2+. But it's not. So yes, there are. There aren't as many that do 2 electrons, that have 3 different oxidation states that are relatively accessible and still occur at a reasonable potential. But you're exactly right, Tim. There's lots of them that will do those, but somehow they change the structure so significantly that they actually degrade, which is the other problem we have. So it's each material has its own chemistry, its own story, and so some of those work well, and the vanadium seem to still retain a layered structure and still accommodate those electrons pretty well.
Okay. And then my second question was, you said another reason that you chose it was because it was an excellent host for lithium. But if we're trying to move away from lithium and more into magnesium, then why is that a positive?
Well, it was just to say it was a good candidate, right? It had done well with the lithium side, so we thought, okay, maybe we can use it for new materials as well. So it was more like a starting point. What I didn't show you, and I thought, I could have showed you, is how bad normally the crystalline V2O5 actually those magnesium ions. It doesn't actually store well, and I realized I should have just put that data in there, but as it forms these nice layers, it's horrible, right? So lithium was much smaller, so it could go in there a little bit easier, but once we started trying to shove this magnesium in there, it would not go well, and the capacity was very low. So that's where we sort of learned, well, this isn't the same. It worked well for this, we're gonna have to change things a little bit to make it work. It's a great question. Good questions.
Yeah, well, sometimes we just like to let you figure it out.
All right, let's thank Dr. Rhodes.
For more information, please visit tlu.edu.